materials that are used for used in photovoltaic cells are what we call semiconductors. And semiconductors are materials that don't normally conduct electricity but can under certain conditions. Okay, so whereas metals are good conductors, semiconductors, or sometimes they're called semi-metals, are sort of on the boundary between pure metallic properties and non-metallic properties. And so the classic semiconductor is silicon. Okay, and this is a model of silicon. So these are the atoms of silicon. Silicon is in, if you have a periodic table in your room, take a glance, it's in group 4, silicon is. So that means it has 4 valence electrons. And so you see the way, this is a crystal of silicon that's been prepared such that the silicon atoms are in a nice crystalline array. And you can see that each silicon atom has 1, 2, 3, 4. And then the electrons are sort of shared in groups of 8 around each silicon atom. And so what we find with the silicon, it only conducts electricity under certain conditions. So that's the semiconductor part of it. And one condition that it will is if you heat it up, because see, the thing about the silicon is the electrons are held more tightly in position than in other metals. Okay, it's sort of in between almost covalent bonding in a covalent solid versus a metallic solid. And we do have solids that are called covalent solids, where the entire solid is a array of covalent linkages. But in this case, it's sort of in between covalent and metallic. So anyway, so if you just apply a voltage, the electrons may not move. But if you heat up the silicon, or if you add, expose it to electromagnetic radiation of a certain intensity, the electron will be motivated to move out of its position. And that's what's shown right here, is a photon of light is striking this, say, the solid surface of the silicon, and it hit the electron that was right here, and that electron had enough energy to move out of its position into another position. It didn't bounce completely out of the metal, it just caused it to move to a different location. It gave enough energy to get moving through the solid into another location. Okay? Now, obviously, this is happening at the surface of the solid where it's exposed to, in this case, a photon of light. When the electron moves out of its position where it was, it's called a positive hole, because it's left a place where now the charge on this particular silicon atom is going to be slightly out of balance. And when you set that up, you're going to set up a potential which is going to cause another electron to try to move into its place. And then what happens is the electrons then start moving around, more like what's going on all the time in a metal. Okay, so it can act like a metal when it's exposed to heat or light. That's what a semi-metal is. Okay. Let's see if I told you everything I want to say. Okay, so it's kind of like metallic bonding when it's exposed to some energy, either from photons or heat. All right, so that's silicon, and what they found is that silicon is what's used in the semiconductor industry for electronics, and they found better ways to get the electrons moving, to set up a potential, both in the semiconductor industry and in the photovoltaic cell industry. And what they do here is they dope the silicon with other elements that either have one extra electron or one fewer electrons. Okay, and for example, we said that the silicon is in group 4 in the periodic table. It's just under carbon in the periodic table, as a matter of fact. To the left of silicon is aluminum, to the right of silicon is phosphorus, and below silicon is germanium, to the right of that is arsenic, and to the left of that is gallium. And silicon, germanium, gallium, arsenic are all semi-metals. Going down that stair step, so this is in group 3, this is group 5, and the group number, remember, is telling us the number of valence electrons. So what happens is then the silicon has been doped. That means they've added, like on the order of parts per billion, amount of either gallium or arsenic. When you add gallium, since it has one fewer electrons, let's see, here's a gallium, here's an example. Since it only has 3 valence electrons, then you introduce a hole, okay, into your silicon crystal, and so it allows the semiconductor to be more of a conductor, okay, because already there's a place where an electron can move into. Alrighty, and so that's called a it's actually called a p-type semiconductor, because you are opening up and having one fewer. Once the electron moves away from silicon into the gallium, the hole by gallium, then the silicon is going to be missing one electron, and it's going to temporarily have a positive charge. So it's called a p-type for the positive charge. And then over here, this type of semiconductor, in this case arsenic, has been doped into it on the order of parts per billion. And that introduces an extra electron that doesn't really have a place to be, so it's going to want to kind of float around. And everywhere it goes, whenever it moves away from the arsenic and around a silicon atom, then the silicon atom is going to have one extra electron around it temporarily, and that's going to set up a negative charge. That's why, excuse me, this type of semiconductor is called an N-type semiconductor. Okay, so this is out of research and development, how to make a semiconductor more conducting. You can dope it, and you can dope it with these different metals, gallium and arsenic, and there's others as well, but these are the 2 good examples of it. All right, and so then to make your photovoltaic cell, what the engineers do is they sandwich the N and P-type semiconductors together, and when you do that, that creates a voltage, which will generate a direct current. It's directing the electrons in a certain direction. They're going to want to move from the positive to the negative hole and around. Okay, they're going to be directed around from where there is an extra electron around this circuit to do work. Okay, so this is just an example of what a solar cell. Thinking back to what you saw at the very beginning in this picture, this thin device here, this solar cell. See, they're thin with a large surface area because the sun has to hit it in order for it to work. So this would be a sandwich of just the glass plate on top to protect the whole thing, and then something to hold the glass on, some sort of adhesive, an anti-reflecting coating, because the light that's reflected or absorbed and turned into heat is not going to be used to move electrons around, so you want to try to maximize the efficiency there by reflecting a little bit, as little of the sunlight as possible, and then the sunlight hits the N-type, and then gets the electrons moving, and the electrons, it's easier to move through the low resistance electrical wire back around to the positive hole, so it moves the electrons around in this direction. All right, they're circled around in this direction because it's easier to go this way than to go straight that way. All right, so this is just an example of some basic concept of a semiconductor that has metallic bonding-like characteristics, which have been enhanced by doping the silicon crystal with either an element that has an extra electron or an element that has one fewer electrons in its valence shell. And the engineering of setting up the external low resistance wire so the electrons will move around in this direction and give some direction to the electron movement, which can then be used as to work. Okay, so obviously the sunlight is free. The thing that's expensive here is creating these materials. So in the next part of this lecture, we're going to look at if sunlight is free, and this is obviously very clean, there's no emissions coming out here or anything. We're going to see why currently the energy market is only 1% solar voltaic cells. So we'll look at that the second part of this lecture.